Hello everyone, we are live again. This is Highload of Fwdays conference, and we continue with our talks. So right now, we are great to see that Jan Cooper is here, and Jan, hi, how can you hear me?
Hi everybody. Yeah, I can hear you now. We were struggling with the usual pandemic difficulties of devices, but we're good now, I think.
Yeah, well, great. It's great to have you here, Jan. Thank you very much for deciding to do a talk at our conference for the first time. Unfortunately, right now this is online, but we believe in a year or so we will be able to do our conferences offline again, and we will be really great to see you here in Kiev again. I know that you've been
Yeah,
here for a
fantastic.
couple of times, right?
Yeah, I've been here. I've been here a few times before, and the company I work for in the UK, Just Eat, has a office out in Kiev as well. So
Okay. So yeah, I think it would be great if you visit Kyiv once again and another conference. So
yeah, I'd love to.
there are some. Our technician guy is asking if you could move a bit back so we can see your head better. Yeah,
Better?
great. Perfect, perfect. So thank you. The title of your talk is Event-Driven Collaboration. And by the way, I'm sorry, I haven't introduced you properly. Jan Cooper is polyglot coding architect who is based in London. So, Jan, let's start with your talk and wish you luck with the technical. I mean, I wish you so everything goes well technically.
Yeah, I hope so too. I'm sure we'll be fine. Great. Thanks very much. Um, Hello, everyone. Today I'd like to talk about the topic of event-driven collaboration. And really what that means is that when we decide that we want to use messaging, middleware-based messaging as the means of communication between various processes, often nowadays microservices, uh, although that may seem like I just get the messaging middleware and send messages, in reality, to make that work requires knowledge of a number of patterns and practices that we have to understand to be effective. Okay. So you can find me on Twitter at the bottom kind of link. If you have any questions afterwards and you don't get a chance to hear them here, I'm very happy to talk you through them. This is me. It's kind of dull. It mostly says I have grey in my beard now. I often draw attention to the bottom point. I'm fortunate enough to have begun speaking to an internal user group, got some confidence about being able to present technical topics, but I'd encourage everyone to really give it a go. And I think that as a practitioner of software development, this notion of you see one, you do one, you teach one does really help you organize and clarify your thinking, and you get to go, interesting places. The other thing to mention, if any of you are .NET developers or even actually Python developers, I am the founder of an open source project called Brighter, and Brightside's the Python version that helps you do messaging. It's a framework that sits between you and the various middleware transports and simplifies the process of using them, making the experience very similar to using, say, stuff to write basically an API and HTTP, trying to get that level of simplicity for you. All right, what are we going to talk about? Actually, the first item we're going to talk about a little bit is just a tiny review of microservices. I don't want to make this a microservices talk. You didn't come here for that. But I want to set the context so we have a kind of similar definition because it will become important to us a little bit later. We'll talk a little bit about the part in there, this idea of what we call data on the inside versus data on the outside. And that will become important to us when we look at certain techniques we can use to solve messaging problems. We'll look at request-driven architectures and event-driven architectures. We'll understand when we might want to use each. And then we'll look at two key things you'll need to understand for building an event-driven architecture: the use of pipelines and the use of reference data. Finally, we'll end with a little discussion of correctness, which becomes important to you if you want to use some of the above techniques, and how you can get correctness between producers and consumers. So I originally started my career in sort of distributed systems back in the 90s. And in that era, really, we were talking about things like Corba, Complus, and Decom. In the way of the world, everything old is new again. And we were communicating a lot via remote procedure calls between components that were running in different processes defined with an interface definition language. And that's not that dissimilar today to what people are doing, say, with something like gRPC. But there were problems in that era with the technology, particularly something like DCOM. It was very hard to get working. You had to open a set of ports on both machines. It was not always clear which ports you had to open. And as a result, there was a Microsoft developer evangelist called Don Box, who used to speak a lot about COM and DCOM. And he thought to himself, well, actually, port 80 is always open. So maybe I could send this RPC request over HTTP instead of TCP/IP. So he said, well, if I just take the body and make the body of the HTTP request something that says, call this method on the object that's remote, pass it these parameters, and in your response, when you give it back, give me the return values from that method call. And because it was very straightforward, he would basically say, I can call from this one to this one. I can get something that I can generate a proxy that looks a bit like it, you were already calling the object. And on the far side, I can kind of call into the object. He called it the Simple Object Access Protocol, or SOAP. So SOAP was originally a way of getting COM working remotely, but later then people realized, well, you didn't need the COM objects on basically the server side or the client side. You could actually just use HTTP to talk to something running directly on the web. And thus, essentially, the service-oriented architecture revolution was born with SOAP. And it exploded. People began writing these web services everywhere. Certainly in the early days of .NET, when I was a .NET developer, in the noughties, web services, I think also in Java as well, were huge. That was the way we were all delivering these autonomous components. And it let us slice up these huge enterprise monoliths into a number of pieces, which had some benefits, right? They could have their own data stores, etc. Famous proponents of this approach were people like Amazon, who were at the time were really just a retail company selling books and goods on top, who embraced this idea wholeheartedly and effectively built what is now we think of as AWS as a result of this. We then got into the realm, which we'll talk about a bit later, of people realizing that using a remote procedure call-based architecture had some difficulties. And we'll mention what those are later, but we began to move away from that towards events. At first, SOAP moved from the ability to send just RPC requests to being able to send data, what was called document style. In some cases, people then began to embrace things like REST, but also we began to use middleware to send events between components. And that led a little bit to a growth of something we call the enterprise service bus. The vendors felt that they needed to be making money out of this SOA revolution. And so they offered us this hub that would sit at the center of our service architectures and essentially direct traffic from one microservice to another. So you would raise an event and it would decide who to distribute it to. But it would also integrate third-party software. So it would say, well, this thing doesn't understand events, but it's fine, I can deal with this database. This thing's old school SOA1, but it's fine, I can deal with its web service. And slowly over time, what happened was workflow logic crept in there. So we began to run actual business logic in these centralized hubs. BizTalk is a classic example of a product that was in this space. And the problem with that became twofold. The first, it was very hard to use modern techniques on the code that lived inside these enterprise service buses, like, for example, test-driven development. You couldn't really do TDD against code that was often designed with a visual designer with blobs of code at various points. And we also had tied ourselves firmly into that particular vendor. BizTalk now lived at the heart of your application and you couldn't replace it. Jim Weber, who worked at ThoughtWorks, led a sort of counter-revolution to enterprise service bus that he called guerrilla service-oriented architectures. And he said what we should do is move away from this centralized enterprise service bus model and have services tending to talk point-to-point or through a lightweight broker like RabbitMQ. And he advocated things like REST or RabbitMQ or ZeroMQ as being ways of working. And really the idea was what we now refer to as smart endpoints and dump pipes. And those ideas from Jim in Gorilla SOA, coupled with domain-driven design, coupled with DevOps ideas, were merged together as microservices, which was essentially a description of the current best practice around service-oriented architectures by Martin Fowler and James Lewis. And obviously, I thought works were really reflecting what was happening in the wider industry at that time. So it's useful to understand that, because when we think about what a microservice is, it's useful to understand that in some ways it's SOA 3. And some of the original description of SOA and some of the white papers that exist and the deep thinking that was done by individuals in that time window are still very informative if we want to build successful architectures. So this diagram relates to what we call the 4 tenets. The 4 tenets were designed by Don Box, who, if you remember, originally created SOAP. And they're as follows. Boundaries are explicit. So our microservice has an inside and an outside. Inside is where my code lives, my schema inside a database. Outside are where all my consumers live. And the boundary between the two needs to be explicit, an API. Now, when we say an API, it could be any kind of protocol, gRPC, HTTP, AMQP. We are agnostic to quite what that is. Okay. But we must go through the boundary. There must be no direct access. You mustn't be able to talk to my database directly, and you mustn't be able to talk to my code directly. I must be able to vary those independently. And that gives us the characteristic on the left-hand side. Services are autonomous, often rephrased today in microservices land as independent deployability. The idea that I can deploy my microservice without anybody else needing to deploy their microservice. So any changes I make internally to my microservice, provided I don't change the contract with you, you won't need to do any work. And that also gives us share schema not type at the bottom, where we say what we should be sharing is neutral formats like JSON or XML or protobuf or Avro. We shouldn't be sharing things like .NET types or Java jar files in order to define what the contents of our API looks like. And compatibility by policy is one you can worry less about. That simply says, because things like the boundary, it needs to have a given protocol, because I might need to do authentication by a mechanism, then you need to understand, I need to publish that information so that you can figure out how to successfully call me. Those are defined as the 4 tenets. Pat Helland, who worked at Microsoft and then at Amazon on their service-oriented architectures, looked at this and said there are some interesting properties that we can reason about as a result of this. So whenever although my service owns its data and it's in that database that nobody else can touch and you have to come through the API, obviously data exists which relates to, in this case, for example, what the example we're going to use throughout this presentation is about a hotel booking system. So information about the bookings lives inside here. And somebody might want to ask me for information about that booking. So they may say, can you give me that booking information? So the information leaves my service, it crosses over that boundary, and it now exists outside. Similarly, I might raise an event and say, okay, here is an event that describes this booking, and that information now lives outside. And there are some interesting properties about this data that's left the service. The first is that as soon as it leaves the service, it's stale. Although I now have a copy of your booking data, it's quite possible that somebody could now do a post request to the API in front of direct bookings, say, I want to modify the details about that booking, and the information you just obtained via GET is now out of date. Similarly, I might publish a message saying it's created, and there might also be another change behind it which says that it's been updated. If I'm just processing based on the created message, essentially I am working with stale data. And this is inevitable as soon as we have multiple processes that we will be dealing with stale data. Because that data is stale, we often version it. You can see, for example, on the GET at the top, we've said it has a last modified stamp. That's telling us when it was last modified. That's a version, effectively, and e-tag is the same. And we're also indicating how long we think you could trust this data for, right? How long before you should probably ask whether or not you have the latest version of this data. We don't show it directly, but similarly, we could put a version number related to the entity on the event. Okay. The data is also effectively immutable. Okay. Changing the data that we receive by that get or event is meaningless because the only change can be done through the explicit API to the source database. I have to call back into direct bookings in order to make a change. Okay. So we can summarize that as saying that we have a single writer of the original data and that data outside is immutable, stale, and versioned. And we refer to these as inside data and outside data. Let me just take some water. And we do some interesting things with this data, which generally think of as reference data. And one of them is we tend to cache it quite a lot. So I can cache in a number of places. The reverse proxy, which lives server-side in front of my service and says I don't want to do the database walk of shame too often. If the data has essentially already been obtained by me or somebody else previously and is still accurate, I can obtain it from that cache. I may have a forward proxy inside my organization, which says rather than everyone inside the organization making the same calls to this origin server, I will cache one person's call so that another person's call can use that same response. And I can cache also in my own browser when my application is running or where I'm looking at a particular website. And what we're trading is latency for consistency. If I take the data from the browser that has the lowest possible latency, it's there right next to me. If I take it from my forward proxy, I'm probably making a call over my internal LAN or WAN. If I'm calling across the reverse proxy, I'm going across the internet, but at least I haven't gone to the database, etc. Right. But the risk is always that I have some consistency issues, and so I may have strategies to work around that, such as, for example, the way utags and last modifieds work and the request to go back to the origin server and check. Right. So you can see there what we're doing is doing a get booking, and we're saying if modified since. Right. So we're checking to see whether or not the data we have is still valid. And if it is valid, we kind of renew the lease on that cache. And if it's not, we'll get new data and we'll update our cache of that data. All right, let's park that knowledge for a moment and go and look at a second problem. Imagine I have a monolithic system and my monolithic system is taking hotel bookings. I always say, by the way, that I know nothing about software for hotel booking systems. This is all just a guess on my part. I did that a bit deliberately because I find that if I know too much about a domain that I've worked in, I get distracted by the detail. So I want something where I can talk very broadly and feel comfortable. Okay. And what we're going to imagine is a scenario where what I want to do is take a booking for somebody that has an account with us and has therefore has stored their credit card details for future use, so they don't have to keep entering them every single time. So I might post to my API. I might go to my direct bookings module inside my monolith. I might go and write the information about the customer's booking to a database and ask essentially for that customer's account details. Once I have the customer's account details with their credit card information, I might ask my credit card payment system to then take the payment for the customer's stay. And if I get the customer's payment information back, I'll store that the direct booking is been finished and informed housekeeping to book the room out for that customer. I then may go to my channel manager, and that's the thing that looks after sites like booking.com for me and tells me about my room availability, and update them as to essentially the number of rooms I have and even pricing if I think I can create some surge pricing around an event like a wedding or a conference. And the thing that we're relying on here a lot is the fact that we share this database. If I want to, as direct bookings running this process, find out your credit card payment information in order to give it to the credit card payment system, that's very easy for me. I can just reach in directly and do it in process. The problem becomes that as soon as I break this up into microservices that will have their own database, how do I do that? How does direct bookings now ask the account system for my credit card information? How does it tell housekeeping that I've got a booking? Right. Talking to the database is, we know, the wrong thing to do. When we looked at those 4 tenets earlier, they were clear. Boundaries are explicit. Services must be independently deployable. I can't share the database because then you will be subject to changes in the schema. So what do I do? Well, the obvious answer would probably be that I call the API. The API may exist only internally, but it's also quite possible that I have an API that I'm exposing to my clients, my web clients, and my phone already, and I can just reuse that same API. And that seems like a natural progression. And particularly as I begin to work towards breaking up a microservice, it may feel that I can replace this in-process call between one module and another by simply having an out-of-process call and treating the boundary to my original module as the API that I'm going to expose in my microservice. All right, so let's think a little bit more about how that might work and maybe think about what the problems with it might be. So the idea we came up with is that we were going to make a call to an API exposed by our microservice that may well have been migrated from the facade we had over our module in the monolith. But the problem is, what happens if I lose one of those services? Now, this may not be something we see too much if we are still inside a data center, but particularly if we start to move our services to the cloud, where we work on much more unreliable wide area networks, where we have cheap commodity hardware running inside shipping containers that are abandoned when half of the compute units in there fail, we may see more instances where we lose services. Indeed, our uptime is only something like 99.5% on an EC2 instance running in Amazon. So if our channel manager is down, then essentially we can't inform third parties that we've booked a room out and there's less rooms available. And naively, if we don't account for the fact that channel manager's call could fail, we might end up failing the whole booking and saying we can't take your booking right now because we couldn't complete all the steps. And certainly this is quite often happens to developers when they naively translate and process code from a monolith, which never had to account for network failures and don't account for those failures when they talk to an external service. And the business might say that isn't really what we wanted. We're quite used to the idea that we may be overbooking, and if it so happens that because the channel manager doesn't get updated with an individual booking, we get an overbooking one weekend, we have processes in place to deal with that. Generally, we don't expect full attendance for people who actually book with us, and maybe we have an overflow hotel we can send customers to instead. It's even more problematic in this scenario, though, if I say, well, when I try and get hold of the customer's credit card details to take the payment, the account system is down, and I can't obtain their credit card payment details. Do I fail the booking then? Do I return to the customer and say, I can't get hold of your credit card details, can you enter them again for me? And what happens if I can't get hold of credit card payments? Do I say, I'm going to basically suspend your booking? So one of the solutions we tend to use to this is to say, well, one of anything is bad, so I'll have multiple instances of all these services I'm dependent on. And generally the idea is I put a proxy in front of my collection of services and I load balance across them. Something like Nginx will work here, right? And I can say, well, I've now got 5 instances of Channel Manager. So if in the event that one of them is not working or available, that doesn't matter. I'll just route to a healthy instance. And that tends to create the idea that we say, well, I could actually have some kind of health check to see whether those instances are up. And if they are up, I will direct traffic to them. And if they're not, I won't. And I can also think about strategies like a retry. I could say I could put my retries here. And in the event that I can't talk to the channel manager at first, I'll try again in case it's a transient error. And I could even have a circuit breaker, which says I've tried to talk to that particular instance a number of times. It hasn't worked. And I'm going to stop sending traffic to it. And then I'll try again a bit later to see if it's come back to life. All right. And what happens with that is I may begin to think, well, once I've begun to move a lot of these concerns into my proxies, I could think about moving some other concerns in there. Apologies for the slight movement on the letters there on the top. I could move service discovery in, right? If I'm actually accessing my other microservices through proxies here, well, service discovery could take place through the proxy. So I can move configuration up here. I don't really want to have hard-coded configuration in configuration files. Environment variables work, but the trouble with environment variables is they can all reveal my secrets in crash dumps. So maybe I want to move particularly secrets out to some other device. And actually while I'm here, if traffic is all flowing through my proxies, doesn't that seem like a good place to monitor things and run policy? And so I can divide my request-driven architecture up into a data plane where essentially I have all my instances of my services and my proxies, and a control plane which manages all of that. And this is what we call a service mesh. That's all that is. Right? A service mesh is just that next step beyond a simple proxy. And that works, but I can't help feel that I've thrown a lot of extra kit now into the world of trying to keep my services up in my microservice land, and am I really better off than I was in a monolith? The other problem, which we don't show, is that effectively what happens if I change housekeeping? What happens if housekeeping suddenly decides that actually I'm going to break it into 3 services because my hotel software has been exceptionally successful, and now I want to have laundry, room service, etc. It's entirely different services. The problem here is that I don't have independent deployability around that. I must alter direct bookings. I must alter all these parts of my infrastructure that understand the relationship between direct bookings and housekeeping. Okay, so how do events work instead as an alternative? So with events, I have some kind of lightweight broker such as RabbitMQ. What I want to do is essentially send a message to a topic on that broker. I simply say, I'm going to publish a message saying I have a new direct booking. I am then done with my work as direct bookings. I have no knowledge necessarily about anybody else downstream who's going to process that. All of the other services simply subscribe to messages they know how to deal with. So if you know how to deal with a new booking, for example, you're the channel manager, and you know that you have to decrement in the channel the number of available rooms, you simply subscribe to that topic and listen to the messages. If you know essentially how to take credit card payments for a booking, you subscribe and take those messages. And that gives us a couple of key advantages. First is that if channel manager is down, we tend to listen to the broker via what we call a queue that has what we think of as store and forward capabilities. The way I often think about that is this, right? With a request-driven architecture, it's the equivalent really of a phone call. When I pick up the phone and I call you, you have to be there in order for me to communicate with you. If you're talking to somebody else or you're busy right now, or you're not actually near your phone and can't pick it up, I'm going to get frustrated. I can't talk to you, and therefore whatever operation I wanted to carry out with you over the phone now fails. Instead, more commonly nowadays, we'll use something like WhatsApp or Telegram or Facebook Messenger or Twitter direct messaging to talk to each other. Because if you're not there right now, it'll store the message for you and you can get to it. And the same is true with messaging. Right? I can store up the messages while channel manager is down, and when it comes back online, it can process those messages and decrement the room availability correctly. And yes, there may be a window in which channel manager is not available, during which actually those room bookings go out of whack, in which case we can manage those as a normal business problem. But we will certainly eventually become consistent. This is this idea of eventual consistency that we can achieve. And secondly, if I change the structure of my microservices, if I decide that housekeeping is no longer what I want, but I want cleaning and laundry and maybe 5, 6 other services, then what I can do is simply alter those, and direct bookings never has to know, because direct bookings just publishes its event, and cleaning and laundry can come along and start listening. They can come along and start listening at the same time as housekeeping. We can check them in kind of beta and see that they're correct before we even reveal them to customers. So our ability to actually change the topology of our services is significantly increased. And this gives us much truer independent deployability. We said independent deployability is an important characteristic of microservices. Why? Generally, we want teams to be able to operate in isolation from other teams. Microservices are usually a response to the need to scale our organization. And as such, the key thing we want out of microservices is that one team can work, deliver new capabilities against their particular area of the product without really worrying what other teams are doing. So here the team dealing with housekeeping could quite happily break up their service, launch a whole set of new smaller services, probably organized around individual teams, and no one else has to care about that challenge. That's what we call behavioral coupling. And the previous issue that we talk about essentially saying that a service needs to be available, we call temporal coupling. I was fortunate, or perhaps unfortunate enough, was when I first started working in during my holidays from university, in offices that were right on the edge of the era of automated offices. We had about half the space in every floor dedicated towards filing systems, where we kept all the files that contained customers' data. And typically, if you worked in such an office, you would have an in tray and an out tray on your desk. And someone from the mailroom with a trolley would bring you a whole stack of files that they put in your in tray. You would take a file off the desk, you would process it, you would put it in the out tray, and then someone would take that away, and then we moved on to the next person who needed to work on it. And that's essentially how messaging works. It is essentially us automating that whole process. And businesses, quite mature businesses, worked that way for a large number of years because essentially we became independent of failure and were able to reroute steps to new people if required. If someone was out for the day, their inbox just piled up. And tomorrow they came in and they moved everything into their outbox. And really, we're just replicating that model. Okay. So we said that if I took my direct booking, then I could just raise a series of notifications and downstream systems would be able to act upon. So imagine that I've created this new booking and I want to take a payment for it. The customer's details are held on account, so they haven't provided the credit card details as part of the booking. We want to actually take the payment for them and book their room. So we raise a message and the credit card payment listens to that message and it says, I want to take your payment. But the problem is that if the direct booking doesn't have the customer's credit card details, where do we obtain them? So one answer that many people give is, oh, in receipt of that notification, I make a call to accounts to obtain the credit card details, and then I use it to take the payment. But we've already established, haven't we, that we don't want to do that. Because our problem with doing that is that we now have a request-driven architecture again, and we're back in the world of temporal and behavioral coupling. So what do? The answer is the same as when we get something like the observer pattern. In the classic observer pattern, we listen to notifications and we receive one, and they're either skinny or fat. Right? And fat messages say, you don't have to call back. I just give you all the data that you need to process it. And so with messaging, really what we want to send is fat notifications more than thin notifications, because we don't necessarily want you to have to call back. So one answer is simply that the information that goes to credit card payments has all the data we need. It has the credit card details. And the other answer is that credit card payments has a cache of accounts information that's able to consult to get your credit card details. And we'll explain both of those now. Just let me skip past that. I think I've duplicated some slides here. 1 second. Sorry about that. Right. Okay. So choreography. Choreography is the process by essentially which we can create a pipeline of work. Think of the classic pipes and filters architectures that you're used to. And what we say is when we receive a direct bookings message, we call it something like direct booking made on account, and the account system listens to that message. The account system can then enrich that content. It can add the credit card payment information to it. Then it pushes that on to credit card payments, and credit card payments essentially can then take the payment. And if there are errors, all that happens is, for example, we can't take the payment. Credit card payment simply raises an error message. We listen to the error message, those error messages in direct bookings and say, hey, I received an error. And then we can effectively suspend the booking and maybe talk to the account system and email the customer and say, hey, can you present basically an alternate payment method? And we call this process choreography because no one central is in charge. It is simply each system listening to events and raising its own events in turn, but the sum of all those listenings and publishings equates to a workflow that we can then run. But because there is no central definition of that workflow, it's very loosely coupled. We can alter that workflow at any point, and no one has to be the wiser other than the participants in the steps that are affected. It does create some problems for us, and they're the classic problems of a pipeline, such as observability. How do we know what stage we're at? We can often use a thing called a wiretap to listen on the messages and try and determine what state we're at. The danger, of course, is the wiretap forms a point of coupling, which tends to know about the workflow. If we must know about the workflow, what we can do is try some different approaches. Now, some people tend to refer to the routing slip as an approach we can use to try and manage the workflow. I want to dissuade you from using that term. Routing slips really are about the situation where we only have point-to-point queues and no broker, and the point-to-point queues need to understand the direction to send the traffic in. And it can help with this situation, but essentially it's really doing nothing different to what choreography does. More important to us, perhaps, is to think about a technique called orchestration. Orchestration says, I need to run some kind of process manager. And the process manager essentially receives this request for a booking, and it stores something inside its database to say, this user is trying to make a booking, and it calls a direct booking service. And it can do that by sending a message via our broker saying, hey, someone wants to make a direct booking. Direct booking saves the information to its database, and then it can respond. It tends to respond again via sending a message over another channel. Quite often when we make the booking via the process manager, we say reply on this channel. And it tends to give us a correlation ID. Using the correlation ID, we find the session that we already have in the process manager, and we say we've made the booking. Now what we need to do is collect the account information in order that we can pass that onto the credit card system. So we then send a message via the broker to the account system, which then responds with a reply message saying, hey, here is the account details for that customer, and it has the correlation ID, and we wake up the process. We may be sending the same message in each step and asking it to fill in more details. We may actually send separate messages and have the process manager orchestrate everything. We can then take basically credit card payment by using the same process, send a message, credit card payment listening for those messages. It takes the payment, and then it basically responds on the reply channel we indicated to it. When we get it back with the correlation ID, we know that the process is complete. Okay. Now, because of the coupling in the process manager, this is sometimes less desirable than choreography. Because now if I want to alter the way the flow works, I'm going to have to go into the process manager and create a new workflow. But it does have some benefits. One of those benefits is that we know when an error has occurred in something like credit card payments, that we are going to get reversal. Other than relying on events being transmitted which might go missing, the process manager will effectively keep retrying until essentially it ends that process. And that can be important to us if what we are doing is reserving resources for your booking that we're not giving to other customers and therefore not earning revenue from them. This leads quite often to an idea called the reservation pattern. Because when we make the booking, we reserve some resources, perhaps for a period of time, perhaps until your transaction basically reaches a state where we want to reverse it out. And at some point during the process where we experience failure, we may say, hey, I'm going to unwind your booking, and I'm going to essentially make that available to somebody else. So say, for example, for some reason we couldn't get hold of your data, or for another reason we basically kept retrying to use your credit card, etc. So process managers help us cope with this issue of reservation. Generally speaking, they prefer choreography to use of the reservation pattern, the process manager pattern. Okay. And one of the reasons we want to avoid this orchestration approach is given at the top. There's a tendency when people do orchestration for them to shift into this model where they have entity services that just do CRUD over individual entities in the data store, and all the workflow creeps up again into the center. And that's the problem we have at enterprise service buses and SOA2. We don't want to go back there. Better is that each process does some work and raises a message at the end of that work being completely done, not needing to deal with that message anymore. Right? And that allows choreography much more. Okay, so the second problem, remember we talked about reference data right at the beginning of this session. The second idea was that we would build a cache of data to get the information from. So here, this idea called event carriage state transfer says that accounts is going to be raising events. Accounts is going to be raising events to say that a new account's been created, that the customer has moved address, that the customer has updated their credit card details. And downstream, as part of our credit card payments microservice, as well as our HTTP interaction, which lets you actually take credit card payments, or even one that works by messaging directly. We have a worker component that says, I'm going to listen to messages from accounts. I'm going to update a local cache that you're going to store that account information. We show as a separate DB here, but it may be part of the same database server or instance belonging to credit card payments. It may just be a set of tables. You may even merge data in. It doesn't really matter. But the idea is that I listen to that account information. So I store a new account that's created. I update it when the address gets updated. I update it when the credit card information gets updated. And then when credit card payments receives an event saying, please take a payment for this booking, it reaches into the account system to get that cache, to get that data out, and then proceeds with the booking. And because it's a read-only cache of data, because it's outside data I'm caching, it's perfectly acceptable. I'm not bound to the schema. I'm not preventing accounts from being independently deployable and moving forward. But it also means I don't mind if accounts is down. I can continue to take bookings for customers that have an account with us, even if the accounts system is currently down, perhaps for maintenance. Existing customers should not be stopped from taking bookings because accounts is not available. Obviously, new customers can't create accounts at that point, and I wouldn't have their data effectively because you're not generating it for me. But I'm continuing to work with existing customers. And this resilience, this notion of having a bulkhead against failure, is exceptionally important. It's one of the ideas why event carrier state transfer is a very successful pattern. Until I'm a rated event at the end. Reference tokens have used various protocols over the years. Event carrier state transfer is the modern form. At some point, we used atom feeds raised by services. Lots of banks used to do this the whole time using ETL. The only constraint with the ETL is essentially that you'll need the same database on both sides, but they quite had a master that would update something and downstream copies. And FTP essentially, but nowadays you can do that with things like S3, right, which is extremely reliable. Ignore that. We've seen that. We've seen that. I've got some duplicate slides. Sorry about that. Okay. It's important to note the reference data that what we're really caching is stuff where we have our own rules about how that data works. We're not copying rules from the other service about how it modifies or updates that data. If we copy the rules between two services, then we end up coupling them semantically, right? So don't do that. You want data effectively that you have your own interpretation of. Correctness, we'll just cover this reasonably quickly. So one of the problems we may get when we think about particularly event carrier state transfer is that I want to make sure that the upstream and the downstream are correct, right? So if I have an order upstream, then the order exists downstream, or perhaps better if I have a customer upstream, that customer exists downstream. How do I make sure that happens? There's a danger nowadays that if I write something to the table and then try and send something to the broker, that call to the broker would fail. We don't anymore exist in a world where I tend to have basically a two-phase commit between these two items, between the broker and the table. And so the problem can be that there's no transactional guarantee that will work. And even if we did, it doesn't scale very well. So what happens? How can I avoid this problem that if my call to the broker fails, what should I do? Do I suspend the customer's booking? That's probably not what I want. And in some cases, I may not know that the response from the broker may be asynchronous for a while, that essentially that has failed. Number of patterns we can use. The first is the Outbox pattern. That's very suitable if you have an ACID properties database that you're talking to. You write both the order or the new customer and effectively or new booking details to essentially the table, along with essentially in an Outbox table the message that you intend to send downstream. And you do one or two things. You either, and it's my preference, you then send that message to the message broker, and when you get confirmation the message has been sent, you update the Outbox table and say that message was sent. And then essentially you have a service that runs in the background, which looks at the Outbox table and says messages that weren't sent in a certain time window, I will resend. Or essentially you say, I'll just put it in the Outbox table, and that service that runs out of process will just send everything from the Outbox table. It doesn't look as though it's been sent. Okay. I do that less because it ends up with the Outbox table really acting like a queue if you do the second one. Okay. And that means we will eventually send that message. Because we don't always know whether the failure to update the table was due to the fact that the message broker didn't give us a correct response, but had actually sent the message, we may always risk sending duplicate messages. And that means downstream you have to deduplicate by either being idempotent or keeping a store of messages you've seen and checking for the ones you've already seen. Log tailing. If you don't have an ACID database, your best option is log tailing. where essentially you can get a transaction log which shows you all the inserts and updates and deletes of the table. You simply listen to that transaction log, and as you see transactions, you then send them to the message broker. And you effectively treat that transaction log as a queue of work to process on the message broker. And particularly useful with things like AWS DynamoDB, where you can get a Lambda, which essentially gives you the information out of the transaction log. State change capture is the easiest, although it has some side effects. And that's essentially where we write to the message broker and then listen to the message broker ourselves, as well as the downstream listen to the message broker and write the data to the table ourselves. That works very well, but the danger is we may actually see the update to our upstream service after the update's been seen in the downstream service, which can lead to weird effects for the customer, like seeing a notification that they've been charged when they haven't got confirmation of a booking. Okay, logs versus queues very briefly. There are two types of messaging system. One is essentially a shared queue. On a shared queue, something like RabbitMQ, SQS in AWS, I delete a message after I've read it off the queue. Its goal is to be used for notifications. The problem you have is that essentially you can't resend easily unless you regenerate messages from your origin. So you tend to have to use something like an Outbox as a store of messages that you've sent to be able to resend. And when you do resend, you tend to be often broadcasting, which means every subscriber gets those messages, right? There's particularly a problem if you want to introduce a new service that needs a cache of its own. The problem you'll hit is all those services effectively, or the existing service will see messages for accounts they already have updates for. So you will need some form of deduplication. The other alternative is to use a message log such as Kafka, in which case, essentially, because you retain the messages in the log, particularly if you use infinite retention and compaction, new consumers can simply start at 0 and read the whole log and catch up. Older consumers that have missed messages can simply adjust their pointer to read the messages they've missed. And so for scenarios like event carriage state transfer, you tend to want to favor message logs. All right, almost there. Just a note that there's a pair to this presentation called event carriage, called service consumer patterns. And that deals a little bit with what happens at the front end when you have the division of your database into separate microservices. Here we've dealt more with what happens at the back end in terms of processing, but in terms of querying, etc., that presentation talks more about that angle. Okay, and we are done, I believe. And we have any time for questions, I guess. Oh, hello.
Hi, Jan, and hi all. Thank you for a great speech and slides. And it is a big pleasure for me to ask questions to you. So the first question is very simple. How's the weather in London? It's good. Do you hear me?
It was, yeah. I think that, yeah, this, I've given this talk a few times in different places, but I've definitely given this talk in London, I think, before, yeah.
Oh, okay, in the sense of just they said that you are and work from London, but okay, it's not a big deal. And I have a question to you. What are the main pains in event-driven architecture, and how you deal with them each day?
So the main, there are a couple of problems people, as they move towards event-driven architecture, will always begin to hit. The first is that it changes your perception of the system, because generally, as a developer working on an individual service, what you now have is a boundary where you raise messages, but you don't really have understanding anymore of what happens to them afterwards, particularly in larger systems. And some people find that uncomfortable because they quite often find they don't understand how the whole system works anymore. It can be very convenient if you have a lot of microservices, because on your machine it's a lot easier to run your one microservice and check that the events come off it than to try and run the whole of your microservices estate on your one machine. But it can be for some people quite a disconnect to not suddenly see everything. The second one really is that there are certain near real-time scenarios that are very just difficult to get working, particularly if you have some kind of consistency issues where what you're trying to do is, say, update the customer, for example, the running price of their basket, given offers, everything else. One of the problems you can hit is that if you raise every time a customer adds an item to a basket, a whole series of messages, then if you were to show every updates as individual systems completed, you could get inconsistent data at various points. And that's where you need to use techniques like orchestration to essentially capture the whole flow so that you can present consistent information back to the customer.
Okay, thank you for your answer, and I understand that event-driven architecture adds some complexity to understanding and even to our work, and maybe you'll cover this question, you'll answer it, and how to deal with concurrency in event-driven architecture. So, for example, to users who want to book a one-room number and how to correctly handle this situation.
So the reservation pattern, which we mentioned earlier, is one of the key techniques to use, and that works in a number of scenarios. You say, given there's a resource that many people might want, I need to book it for a window of time. And at the end of that window of time, I need to reverse that out. And you can do that with choreography as well as orchestration. So I can simply say, I'm going to raise an event from my service to usually a service that you've got some kind of scheduler that said, or a delayed queue that says, in 15 minutes, ping me again and say that this transaction should have completed. And either I will have completed the transaction, all the events were fired through, I will receive some notification from the last thing in the sequence that says, we're done, the booking has been made, or I won't. And if I don't, and I receive that timer message that says, you should have completed by now, I say, okay, I'm going to basically reverse that out. I'm going to free up all those resources for other systems to use. And if I again get a message saying you've completed, I will ignore that because actually your transaction has failed. And I will probably send a message downstream to say, hey, reverse all the parts of that transaction you did because it failed. That tends to be how you deal with. Go.
I've got it. Thank you. And one more question from me. You said that services, microservices may cache data from another services to use it. Where do you do usually this? You store this cache in some relation databases or Redis or something else, and how to prevent a big amount of the same data that I use in
So you will get data duplication. Martin Fowler talks about this and says that it's a technique that's become more viable for more people because the cost of storage has dropped down. Typically, I see this data going into key value stores. It may be something like Redis. It could be something if you more expensive like Dynamo. You may want to at times completely blow that cache away and rebuild it because the upstream has changed what information they're providing, and you want new versions. So something that essentially is amenable to that. You probably don't need a relational store because you tend to understand that you're looking up by a given key to get some value out, and that you don't tend to ever be querying it.
Okay, I've got it. And can you tell us about your technology stack? You said about Rabbit, Kafka. What else are you using in event-driven architecture?
So I've done this at different places. So when I was more data center focused in an older role, we tended to use RabbitMQ for notification style messages, ones that essentially after I've read it, I tend to delete it. I don't need it anymore. And we repurposed Event Store, which is a database to do the shared log stuff, although I probably today use Kafka to do that. Current place I am, we use SNS and SQS notifications, and we're looking to use Kafka to do the log-based system. Kafka is nice for log-based systems because it has these characteristics of infinite retention and compaction. In other words, I will keep your data forever, but I will only keep the latest version for a given entity ID. So I reduce the cost of that storage, and anyone can go and read that. I haven't really ever played with it. Some people have got this idea of inverting the database, where they essentially build a database directly using something like KSQL over the Kafka log, which might reduce the amount of duplication of data that you need to do ECST, but it's not something I have much direct experience with.
And a question: is it possible to have the same storage for all services, at something like cache service, cache storage for all services, to prevent this data duplication?
Right.
Or
Yeah.
it
No,
will
I've
be a
seen.
bad idea?
Yeah, it'd be a bad idea. So I've seen this before. So the problem is that one of the things you want is for any individual microservice to be independent of other microservices. So if we share a cache between multiple microservices, the problem is that we are all now dependent on that one microservice. It's a single point of that one cache. It's a single point of failure. What we actually want to do is give everybody their own copy of the cache, and then essentially if one microservice is down, it doesn't necessarily inhibit the rest of our flow from working off their own caches. So yeah, and this becomes a problem if you end up with your microservice estate being too fine-grained. So Uber's been talking about the problem of having had too fine-grained a microservice architecture recently, because then you will have a lot of caches of data. And one of the things this pushes against is that it says you want to be this kind of middle ground between old school, very fat services, but you don't want to be too fine-grained on somewhere in the middle, because otherwise that it is going to be unmanageable number of copies of the data that you have floating around.
Okay, thank you. I've also got it, and I think that the time is over. Yes, for me.
Yes, this was a great talk, and thank you for asking and answering questions, Yegor and Jan. Jan, thank you very much for dedicating your time to our conference again, and I hope to see you in the future. So we continue with the lunch break, and I'll switch to Ukrainian.